All right, I think we're ready to get started. So welcome everyone, and thank you for joining us today for our technical meetup event, which, as I'm sure you all know, focuses on scaling network infrastructure. So I'm very, very excited to be here and to welcome you all. It's been a while since our org has hosted a virtual or any kind of meetup event for that matter. We have a great lineup of speakers for you today. First, let me introduce myself. My name is Julia Averbuch. I'm going to be one of your hosts today. I have been at LinkedIn for almost 6 years now. I'm based in New York, and I manage several service infrastructure platform teams in New York and Bangalore. So service infrastructure's mission is to empower all of LinkedIn to build and maintain performant and scalable products and services using state-of-the-art technology. And our charter includes many things like gRPC, GraphQL, service discovery and load balancing, network traffic management, among many others. As LinkedIn is growing fast, so is its scale and complexity of its infrastructure. So today we will cover some topics on how LinkedIn and other tech companies like Solo handle the challenges in managing network infrastructure at scale. So now I'm happy to introduce my co-host for this event, Jingping, who is an engineering manager for the team handling traffic and network policy across trust boundaries. Over to you, Jingping.
Thank you, Julia. My name is Jianping. I'm the manager for the Gateway as a Platform team. Our team is in New York. Our team's vision is to empower LinkedIn services be able to access any resource securely and efficiently with minimal effort. So what it means is that we are dedicated to providing consolidated solutions for LinkedIn engineers to manage the traffic and network policies. So our team owns the LinkedIn egress traffic proxy that we have over 200 LinkedIn services as our client to access the third-party provider in the external network. And as LinkedIn grows rapidly, the scale and the complexity of the LinkedIn's microservices grow very fast. And we are also working on some improvement work for LinkedIn's service discovery and load balancing solutions. If you are looking, if you're interested and looking to learn more about our team and LinkedIn, please join our breakout session after the talks. So let me bring Julia back to talk about the housekeeping rules.
All right. Thank you, Jingping. And these are just some of the housekeeping rules you should be generally pretty familiar with from general, attending many Zoom meetings, I'm sure. But here they are. So first of all, just check on the upper right corner that your view setting is set to speaker view. That's just for the best experience. As usual, please keep your microphone muted, except for the later time during the breakout sessions and other networking. If you want to ask one of our speakers a question, please type it into the chat box. And in case you would like to do it anonymously, you can select LinkedIn support instead of everyone in the to field. And again, just a reminder, after our speaker session, there is a great opportunity to network with LinkedIn engineers and speakers in the breakout rooms. So that's coming up later. All right, and back to Jingping now to go over the agenda.
Yeah, thank you. So today we have 3 amazing speakers in line. We'll talk about the challenges and the solutions in network management. First is our speaker, Ram. He's the director of the field engineers from Solo. He will talk about the most recent innovations in the service mesh management. And our second speaker is the senior engineer, Arib, from the Gateway as a Platform team. He will talk about history of the LinkedIn's egress traffic proxy and the improvement we made in the authentication mechanism. Our last speaker is Sanjay from LinkedIn Traffic Infrastructure team. He will talk about how their team successfully scale up the service discovery and load balancing solution for over 100,000 services. And lastly, don't forget the breakout session for you to ask questions about LinkedIn or Solo. And please join our break session after the talks. So with all that said, let me hand over to Ran.
Sure, thank you. Let me share my screen. Okay, you should be seeing my slides. Give me a thumbs up. Cool, awesome. Well, thanks again, Jingping. My name is Ram Benham. I'm one of the field engineers at Solo.io, and here today I'm going to talk to you about the state of current service mesh today, some of the innovations that are happening, and what to look out for in terms of adoption patterns and growth as you scale to large environments. I work for Solo.io. We are an application networking company. So we have subject matter experts and leaders in the Istio and Envoy community, and we offer solutions on top of Istio and Envoy. So things like Enterprise Istio, Enterprise Envoy, API Gateway, and then things around that cloud native ecosystem would be our subject matter expertise. So like I said, I have a lot to cover today in terms of service mesh. So I'll start with day 1 and day 2 operations of when you first start off with the service mesh and running in day 2 operations, and then I'll talk about some of the innovations that are happening in this space. The big news today is that Istio has been accepted as a CNCF project. Istio's always had a vibrant community of contributors, like companies like Google, IBM, Solo, Red Hat, Cisco, VMware. There's always been a lot of companies contributing to it and a huge set of end users that adopted, but everyone else always asked, why is it not part of CNCF? Is it owned by Google? What does it mean for the health of the project? And I think like those concerns are finally put at rest now that, today officially it's been announced that CNCF has accepted it. And also like this really establishes and solidifies Istio as the de facto service mesh and has won the service mesh wars, just like Kubernetes has won the container orchestration war. So it's a big announcement, and now the community can really focus on building innovation on top of Istio. For those who are not as familiar with the service mesh or Istio service mesh or just general service mesh, I'll summarize that the main features that users go to service mesh for is to improve their network, network on top of Kubernetes or network overlay on top of Kubernetes and other environments. They want to take control over exactly how traffic is flowing so that they can do things like canary-based routing, header-based routing. They can get MTLS in the network. They want to be able to enforce policies on who's able to talk to who. They want to understand the traffic that's flowing, gather metrics, pump it into their observability systems. All of this type of network-related concerns that in the past, we asked our developers to embed that logic into their application code. Now we can tell the developers, no, just focus on your business logic, and then your networking resiliency, traffic control, security policies can all be abstracted away and programmed directly into the network. And that's what a service mesh is. A simplified view of how the Istio service mesh, in a standard deployment model works is that for every workload that is running in your cluster, in your Kubernetes cluster, for example, in a pod, Istio will deploy a sidecar proxy. So these sidecar proxies, and this sidecar proxy is Envoy, and Istio programs all traffic that's coming in and out of the pod to go through the sidecar instead. So now when A wants to talk to B, it doesn't talk directly to B. It, under the covers, proxies through the two sidecars. This gives the ability for Istio to program your intelligence, your desired intelligence, directly into the proxy. So things like retry logic or redirection based on a particular header, MTLS certificates, so you can get MTLS between this sidecar and this sidecar, any authorization policies, all of those service mesh features that I talked about earlier can now be programmed into the proxy without the application knowing about it. And then Istio-D is your control plane that programs these proxies. Istio can also program your ingress, so any traffic that's coming into your cluster and out of your cluster, your egress. And then that is also an Envoy proxy that Istio can program. So as a transparent layer that gets overlaid is how Istio accomplishes service mesh features. A big question that almost always gets asked is, by adding this proxy, what is the latency overhead? To summarize, when there's 1,000 requests going through the proxy per second, we'll see that the Envoy proxy adds a latency of 2.65 milliseconds per hop, and then the proxy takes 0.35 through vCPU and 40 megabytes of memory. So it's pretty negligible for majority of the use cases, especially when you think about the fact that if you were to program this logic in your application code, like in your JVM code, for example, it would be much greater than 2.65 millisecond, 1,000 requests per second. As far as operational overhead, another great question that asks is, how do you upgrade all of these sidecars and Istio? There is a canary style deployment model built into the installation of Istio, where you can deploy different versions of Istio and slowly migrate from one version to another. As you adopt Istio, one of the main use cases that we're seeing, especially recently over the last couple of years, is multi-cluster. Users are adopting multiple clusters, not just a single cluster where all their applications run, but multiple clusters across zones, across regions, multiple cloud providers, etc. And they're using Istio, the networking layer, to kind of abstract away that detail so that an application in one cluster can talk to an application in a different cluster without the traditional leaving the cluster and coming back in. So Istio gives you the ability to kind of group together your services and give it a globally addressable name. And then Istio can take care of the routing capabilities between one cluster to another. This does add, there is more operational element that goes into this so that, the orchestration is all there from a service discovery perspective, but that's where a management plane comes in and helps you orchestrate multi-cluster, multi-mesh patterns. So that's what we've seen at scale, is that users will use a management plane like the one with Solo's Glue Mesh that can help orchestrate all the Istios across their various clusters and then build multi-mesh, multi-tenancy models into it. This allows you to treat clusters as basically just cattles, where you can pull up more clusters as required and then not have to worry about reprogramming the network. Your application teams can just add more clusters and it would just become part of the mesh, and failover, retrying, service mesh configurations are all propagated seamlessly. So that's the current state. So next I want to talk about what are the innovations that are happening in the service mesh space. Most of the innovations are on the data plane side of things. So that sidecar proxy that's sitting next to each one of your workloads. The control plane has matured, the API has stabilized, users are happy with it, and the API hasn't changed much. But the data plane, the latency, the performance is where improvements are happening. The first thing I want to focus on is that latency, the optimizing the data plane path, and which is this piece on the bottom. What the community is working on right now is leveraging eBPF to improve the performance of the IP, the traffic redirection that is currently happening between the application and sidecar. So these two lines right here, how can we make that faster? And what the community is working on is using eBPF to, eBPF, by the way, is think of it as a hook point into the kernel that can attach to various events. And some of those events can be, network traffic. So these are kernel functions that execute at a very low level. We can use eBPF sock map functionality to basically skip this IP tables redirection stack that Istio currently uses. So this is where Istio IP tables redirection happens inside of a pod today. But in the future with eBPF, future and currently, this functionality is in alpha. You can use eBPF sock map to do the redirection, and we've seen a good percentage of latency gain for majority of the applications. The next bit of improvements that are happening are around the placement of the sidecar proxy. So, I've talked about implementing all the service mesh functionality directly in your application code, which is on the left, which is what we don't want because that adds a lot of burden to your developers. On the complete other side of things is you can develop a gateway where all the traffic has to come into every time you want to talk out of the application. So there's a happy medium in between, and that's what the community is working towards. So there's the sidecar proxy, which I talked about over here, and then there's a shared domain. So if we were to dive into this in a little bit more detail, so this is the current model right now, is that every pod has an Envoy sidecar proxy. From a resource overhead perspective, this is a lot, right? Every Envoy, every pod is a lot of resources, but you get a lot of feature isolation because every pod can configure their Envoy this way they want it. And there's a lot of security granularity because the security boundary of every Envoy is just the pod itself. How do we tackle the resource overhead? Well, you can do a shared proxy model where you deploy a proxy per node, per Kubernetes node, and that helps with resource overhead. But then you have a shared proxy, a noisy neighbor problem where everyone's talking to the same Envoy proxy. One feature for one pod can have impact for another feature on another pod. So you have a noisy neighbor problem. So you can start doing intelligent things like maybe do one proxy per service account. So there's now starting to be like a happy, balance between everything. And then there's also the model of taking out the layer 7 proxy, taking the proxy and splitting it based on what features you need. And that's exactly what the Istio project announced last week with Ambient Mesh. This is a project that Solo and Google have been working on for the last year or so. And what we've done is we've taken that Envoy sidecar proxy and we split it. We split it to layer 4 and layer 7 functionality. What this allows you to do is take advantage of exactly what features you need and only deploy the pieces that you need. So I can go into this in more detail in the Q&A if people want me to, but essentially we reduce the number of proxies that are operating in your system by deploying components that are shareable in a multi-tenant way, and then deploy the layer 7 things when you need it also in a multi-tenant way. The last bit of innovation I want to cover is around GraphQL. For those that are not familiar with GraphQL, it's another API protocol. If you're familiar with REST, you know that with REST, you make a call to an endpoint, you get back some data, but oftentimes you need to make multiple calls because the one API call is never enough. So there's usually like multiple tens or even hundreds of API calls you have to make to get back all the data you need. GraphQL solves that problem by giving you basically a server that can aggregate the data for you and give it back to the client exactly what the client asked for. So in this example, the client can say, just give me back the name, phone number, and address of this search query. And the GraphQL server will call all the backend APIs and get that information for you. So it's hugely popular. And the way users are adopting this is they usually facade their existing applications with it. And there's the adoption patterns are, putting one GraphQL server in front of a couple applications and then other GraphQL servers in front of others, and then stitch it all together. In terms of a traffic pattern, now you have two different hops, right? We need the gateway for your security and service mesh functionality. And now you also have this GraphQL server. So to alleviate these two hops, what the community is doing is building GraphQL functionality directly into your Envoy. So whether the Envoy is your ingress gateway or the Envoy is your sidecar proxy, you can build this GraphQL server, the entire GraphQL server, directly into the Envoy proxy, reducing the need for you to deploy your own GraphQL server and just using the Istio Ingress Gateway as your GraphQL aggregation layer. So these are the types of challenges that are coming, that the community is working on resolving in the future. We think a management plane helps abstract away these details and these innovations so that it can give you a layer where you can, in a central place, apply configuration and have it translate to whether it's eBPF or GraphQL config or sidecar config or Istio config, et cetera. So all of those features are just going to become lower level implementation details. And then a management plane is really where it will kind of help you abstract away and start leveraging these higher value functions. If you have any questions, I'll be in the breakout room at the top of the hour to help answer any questions and go into this in more detail. I know that was a lot of information that I covered, but I wanted everyone to take away at least something, and then we can dive into more details later on.
Well, thank you so much, Ram. This has been extremely informative. And to remind everyone, you can ask questions in the chat. Also, since so far I haven't seen any questions in the chat, if anyone just wants to ask your questions now, feel free, and you can unmute yourself and do so.
Can I ask you a question? Really interested about what you talk about the data plane GraphQL, the sidecar one. Do you see any adoption there, as far in the industry?
Yeah,
who's
so
using that model and using a sidecar to deploy GraphQL engine there.
Yes, so we have seen adoption. So what Solo has done is put this GraphQL filter onto Envoy as part of our Glue Edge API Gateway product. And that's where we've seen adoption. We're still working on migrating that over to Istio Ingress Gateway. So that functionality is still very much alpha, but for our Edge API Gateway Envoy, that's already gotten adoption in production.
Okay, and what is the language you use to write that filter? In your diagram, you show the GraphQL filter one in there. And what language you used to code that?
It's an Envoy filter, so it's built directly into Envoy. So I think the language would be C.
Oh, so it's not starting a separate JVM for that.
That's correct.
Because
yeah,
we have GraphQL here, but we are written in Java.
got it. Yeah,
we
I
just
think
trying to
this
see if
GraphQL
there's
server will be written in C.
You are using C to implement the GraphQL server there?
That's correct. Yeah. To the best of my knowledge, yeah.
Okay, thank you.
All right, thanks. I see. So there is a question in the chat. Wasn't the job of Envoy to just sit like a pipe dump proxy? Adding this functionality seems like adding something that it wasn't meant to. Maybe I'm wrong.
I think Envoy started off that way, but there's no reason why you couldn't extend it to do other things. I don't think you should force Envoy to do all of this functionality when it's not needed, but we've seen Envoy being extended to for deeper integrations with things like XAuth servers, web application firewalls, data loss prevention. Users are extending Envoys for all kinds of functionality, either with custom filters, WebAssembly, et cetera. So I think putting GraphQL on there would be a natural extension to it.
Vivek, is your question answered?
Yeah, he said sounds good to me.
Okay, awesome. Sorry, I haven't been monitoring the chat. All right. So yeah, for any more questions, again, Ram will be in one of the breakout rooms, so you'll get an opportunity to chat more. I mean, this is an excellent topic. And so thank you so much, Ram. And now on to our next speaker, Arib, our very own Arib, an expert in authenticating proxy clients at scale. Take it away, Arib.
Oh, yeah, let me go ahead and share my screen. 1 sec. Okay, look good to everyone? Cool. Yeah. So, hey everyone, I'm Arib. Thanks for joining us today at this meetup. I'm Arib, and I've been at LinkedIn New York for just over 3 years now on the GAP team, specifically GAP-in. GAP stands for Gateway as a Platform, and our mission is basically to make the internet accessible to LinkedIn services in a secure and convenient way. Today, I'll be covering our egress proxy, Kraken, and the evolution of authentication mechanisms that it's come to support for our different clients. Just to give an overview of what I'll be talking about today, we'll start by discussing the history of egress proxy solutions at LinkedIn and how Kraken was developed in light of our learnings and previous experiences. After that, we'll be focusing on the primary authentication methods that Kraken uses to identify and authenticate clients and determine what domains they should be allowed to access. And finally, there'll be some time left at the end for Q&A. So let's dive in and start with a little bit about the Kraken egress proxy and how egress looked before it. The first iteration of using an HTTP proxy to manage egress used Squid, which is a pretty popular open source proxy. It filled its function at a basic level, but there were definitely a number of challenges that the team faced with it. One being the fact that it's written in C, which is not really a very well supported language at the company. As a result, the team had like a fairly limited ability to integrate it with our standard tooling, such as monitoring. Such as monitoring. And Squid is still being used by several clients at LinkedIn, but we are now in the process of decommissioning it for good. So in order to address a lot of these shortcomings, GAP proxy was soon introduced. It functioned as a chain proxy, basically forwarding traffic to Squid. GAP proxy added important functionality like integration with our central metric solution at the company and adding ACLs based on an initial connect request between client and proxy. So this let us manage outbound access at a per service level, and eventually GAP proxy was decommissioned in favor of our current solution, Kraken. So Kraken was built on the Java Netty framework, and it's a TLS terminating man-in-the-middle proxy. So it added a number of critical features that we needed, like full traffic inspection, ACL based on the full HTTP request, service-based throttling, and also supported a variety of proxy authentication mechanisms. It can also optionally be used as a tunneling proxy instead of man-in-the-middle mode, depending on our client's use case. And there are a lot of use cases where that came in really handy, and we can discuss that a little bit later. So here's an overview of the basic entities we work with. Our clients are typically other internal services on LinkedIn servers who need to interact with the outside world. Clients will typically make requests to a destination and use Kraken as an HTTP proxy. Kraken itself has two major dependencies: our Active Directory service, which we'll dive deeper into in following slides, and the external domain registry, a service which we use to define egress rules. Finally, in a valid case, Kraken then establishes a connection with the destination through our firewall and facilitates traffic for the lifetime of the connection. Let's move on to how Kraken authenticates clients and determines access to external domains. So we'll start by discussing the first dependency of Kraken, EDR, which stands for External Domain Registry. EDR is used by our clients to define egress rules for their services, which Kraken will consult when deciding whether to allow or deny an outgoing request. Because Kraken functions as a man-in-the-middle proxy and can inspect a full HTTP request, we can define rules based on the request destination, which includes things like the domain, port, and path, as well as the HTTP method. We define these rules on a per-service basis. There's a few reasons we don't use IP addresses. For one, our deployments aren't static, meaning hosts can change IPs without notice. On top of this, multiple services can run on a single host, and we want it to be as granular as possible in defining access rules. Finally, service-to-service authentication is generally a standard at LinkedIn, and we wanted Kraken to have first-class support for it. So our first and primary method of proxy auth leverages client identity certificates to identify a service. So as part of LinkedIn's deployment infrastructure, services are typically deployed with an identity cert, which importantly includes the service name under the SAN section as a URI. When connecting to Kraken, the client creates an MTLS or mutual TLS session, which is where both parties exchange keys. During the handshake with the proxy, the client presents their identity cert and Kraken will verify it and extract the service name from the SAN section we saw before. After authenticating, Kraken establishes its own TLS session with the destination server, allowing it to function in man-in-the-middle mode. This way, the proxy has full introspection into outbound and incoming traffic. It evaluates the HTTP request against the rules defining EDR and determines how to proceed. There's a few important benefits of this approach. For one, most services at LinkedIn are automatically provisioned with these client certs, so there is little effort required of the service owner to establish identity. Second, the whole chain is fully encrypted using TLS between the client Kraken as well as Kraken and the destination, so no secrets are exchanged in plain text. Finally, with this flow, Kraken can function man-in-the-middle mode, allowing us to inspect all traffic. On the other hand, there are some notable disadvantages. For example, for large payloads, this can be non-ideal since we buffer requests before forwarding it to the destination, which can result in memory contention. So for use cases like this, we have tunnel mode. Additionally, not all HTTP clients can readily be configured with the custom client certificate, which leads to our next authentication method. Basic auth is likely the most commonly supported proxy auth method. In this flow, clients typically try to send an HTTP request through the proxy. If the request is missing a proxy authorization header, the proxy returns a 407 error asking for it. The client typically follows up with the connect HTTP request, this time with the proxy auth header, as well as the username password credential pair encoded in base 64. At this point, we perform a TLS handshake with the client and another with the destination to get man-in-the-middle mode again, and function similarly to how we did with this client cert auth. A new feature we've added recently to Kraken is the ability to authenticate using a service account. A service account is an Active Directory entry used to identify a service for authentication and is created with the username, which is typically the service name, as well as a password, much like how a normal user entry would be. Proxy clients can then pass in the credentials for their service account, and Kraken performs an LDAP bind operation with the Active Directory server to verify these credentials. The username is then used with EDR and the flow continues as normal. Basic auth was implemented primarily because it's the most commonly supported authentication scheme, particularly when working with non-first-party code. Some examples are like the request Python library, Azure SDKs, and several other libraries that many of our clients use. Oftentimes, it's actually the only supported proxy auth method. Basic auth is also usable by certain clients who, they might be deployed in they might be deployed in environments that don't have access to these identity certs. And so the username password credentials can be configured using environment variables or JVM arguments when the HTTP client can't be customized. Other benefits have been that LDAP is fairly lightweight for authentication and allows us to leverage our internal Active Directory for a central credential store, and at the same time also allowing Kraken to function man-in-the-middle mode. So our experience with Kraken has been fairly positive. By building our proxy from the ground up, we've been able to develop features and integrations that allow us to manage egress for a very wide range of clients. An important aspect of the development process has been just having an ongoing conversation about these different clients, and which has led to the need to implement basic auth for certain setups. So with Squid Proxy finally being in the process of being decommissioned at LinkedIn and clients moving on to Kraken, it's these learnings and the efforts we put into Kraken that have put it into like a very healthy and scalable state. Thank you. Yeah, we can move on to any questions.
Thank you, Arif. Yeah, it's a great work and very cute picture of Kraken. So any questions? Okay, there's one from Zach.
Yeah.
Yeah.
room for improvements in Kraken authentication. There are a number of authentication methods that. So the problem is a lot of times. So there are better things than username password. I'm forgetting the names of like NTLM or digest based. The problem is a lot of times our clients cannot be configured, or like they'll be using libraries that only support things like basic auth, which makes it tricky. So even though we can support, and we ideally should support these authentication methods, it becomes a challenge to actually get a lot of clients using them unless they're writing their own HTTP client. But it's definitely something that we need to look into as a team to how we can better improve like our security and onboarding experience.
Thank you. Okay, another question. Yeah.
Yeah. So tunnel is like actually how I think a lot of times how a proxy works. It functions basically as an L4 proxy, meaning that when we receive the connect request, we basically just open like a dumb like TCP pipe to the destination. So we still verify the destination and the service name using the info from the connect request, but after that we don't have any inspection, or yeah, we can't look at any of the traffic going in and out because we're not in man in the middle. It's all just usually encrypted TLS with the destination just going through. So that's tunnel mode. And the reason why it's better for memory usage is because we don't buffer the messages anymore. We can just keep forwarding the TCP packets. Any plans to make Kraken open source? Yes, it's I think we have some hurdles to clear there, mainly separating kind of like internal logic out from like an open core, probably. Yeah, we're working on it. There have been discussions. Yeah.
Yeah, we can talk more about that during the breakout session. Yeah, the main thing is how much we can contribute to the open source community. If we see the value there, definitely we should do it. Any other questions? Cool. So yeah, let's meet in the breakout session and we can discuss more there. And let me bring in Sanjay. It's all yours.
Thank you, Juanping, for the introduction. And yeah, hello, everyone. My name is Sanjay, and let me just share my screen quick. I hope my screen is working for everyone. Yeah. All right. So yeah, my name is Sanjay, and I work for LinkedIn's traffic infra team here for the past 3 years. And what basically traffic infra team does is handles the workflow for reverse proxy for all LinkedIn.com incoming requests. The workflow basically includes working for like the login, authentication, or doing all the service discovery and load balancing for all the downstream servers that we are going to talk to. So today we are going to talk about particularly the service discovery and load balancing aspects of the same workflow, and we'll see like how it evolves as we have to scale up our whole ecosystem. So the talk is basically divided into 3 major parts. One is basically we'll have the basic introduction of the concept of service discovery and load balancing, what it means to do service discovery and load balancing. And in the second part, we are going to talk about the evolution of service discovery and load balancing for our ecosystem, and like how it changes as we face challenges of scale, and how we react to it, or how we plan around those challenges to solve. And at the end, we are going to talk about the conclusion of the basically, which includes the current scale and the future scope or the plans that we have in order to meet our future requirements for the site capacity. Yeah. So what is service discovery and load balancing? So as the name suggests, it basically means like, how do I find my service using a name? So in other words, it's basically like, you have to find a server where this particular service is hosted, and all you have is just a name. At the end, it's just going to be an IP address, of course. And how do you cover the same using a name? That's basically the service discovery. So we have two primary objectives here. You have to get the list of all the servers which host that particular downstream service. And at the same time, you have to ensure that the correct state of that server is also maintained, and you are aware about that, whether the server is up or down, and you have to be very particular about in order to make the correct routing. The various, so while doing all this, like, you might have two major caveats around it. One is basically, now all the monolith services are basically moving towards microservice architecture. And at the same time, with increasing scale, you're adding more servers to those microservices, and that puts a direct load on your service discovery ecosystem. And at the same time, the deployment architecture is also moving away from VMs to container-based systems, where the difference is basically the VMs used to take like minutes or seconds in order to start or stop. At the same time, now containers take like literally milliseconds to start or stop, so that your second objective is kind of under pressure, where you have to maintain the correct state in a real-time fashion. So basically, there are very large number of dynamic updates, and you have to react according to that in a very fast manner. For load balancing, it's very simple to explain. Basically, use your resources as optimally as possible. While doing that, you have to ensure that there's a fair load distribution across all the servers that you're going to talk to, and try to avoid all the unhealthy servers, basically, which will lead to the maximizing the throughput for your services. So how does the evolution looks like for service discovery based on all these understanding? So the very basic thing that we can do is basically, the clients can, if they're going to talk to a particular service, they can just simply store all the hard code all the IP addresses that the service is hosted on, and put it in some sort of configuration. And then based on whatever load balancing algorithm that we want to use, it can simply talk to one of these IP addresses. So of course, it looks like a very basic minimal setup, and since it is hard coded, it's not going to scale well. As you scale up more, like I said, like we have to add more microservices, more servers are going to be added or deleted, and at the same time, there will be a very fast updates of the containers. Then this becomes like very difficult to manage, and the manual updates are not going to scale up. And the second update problem can still happen is like the servers can still have failures, even though you know that by definition a particular server IP1 is supposed to be up for this service, and due to some intermittent network issues or whatever, there can still be some failures in between, and this setup is not ready to handle that. So what do we do next? We basically introduce another component called like health checker. What it can do is like it can read whatever you config that you had for your static IPs. It can do a periodic health check on all those servers. So this is again a minimal setup to address the immediate problem, and it can now handle the deletes. Basically, if there is a server IP that is deleted from one of those the service configurations, the health checker will figure it out using the periodic health checks, and it will basically update your config dynamically while on the runtime, and you don't have to update your configuration in order to do the service recovery correctly. This still cannot handle the ads. If let's say your service adds another server here, and there is a server IP4, the health checker has no way to know about it, and the ads cannot be handled. That still needs to be manual. So that problem still remains unsolved, and we might introduce one more problem where the health checker is, since it's doing a periodic health check on all the IPs, if the configuration of that refresh or the health check interval is like too fast, let's say like we want to do the health check too frequently, then it might end up that we are doing too many health checks on all those servers. And if there are like a lot of client nodes as well, then the health check interval can basically cause a problem called like thundering herd kind of problem, where all of the clients are trying to do health check on a particular server at once, and thus it can potentially bring down the server just using the health check. So what do we do next? What we can do is like we can introduce DNS. So now the problem of maintaining the static IPs kind of is eliminated, and you just have a DNS address for your service and talk to the DNS in order to get all the IPs which are associated with this particular address. So add and deletes are both handled by DNS, because DNS has its own mechanism to refresh the information, and it will always give you the correct information. But after introducing DNS, we might run into different sorts of problems now. One is basically DNS has its own caching interval. So that is also configurable. So if you want, let's say, faster refresh, you want have a very, very dynamic server updates, and servers are changing very fastly, then you would want to have faster refresh, and you would consider DNS to refresh the cache very frequently. In that case, there will be a processing overhead because it needs to like update the cache very frequently, and sometimes there might be possibility that the servers are not updating that fast while you are doing unnecessary processing to get the latest data. And if you configure the update interval to be a very large interval, basically it means like a slower refresh, then that's possible that sometimes you may miss the updates, and or it might be delayed in your service discovery ecosystem, and the client may not even know if a particular server is down or up depending on the refresh interval configured. DNS is another problem in terms of scale, where it has a cap on the response size. So if you configure DNS in UDP mode, you'll have like 8 KB cap of the size, response size limit, and in TCP mode, it will have 65K. So while that is like enough for most of the use cases, but I think like this still puts up a cap on our limit to which the DNS can scale, and after some point, it will again run into the same problem, and there will be no solution around it. So this, and we still haven't solved the failure in between problem, where DNS can tell, okay, this particular host is up, and you can send a request to this particular IP. In a healthy scenario, everything will work, but if there is a intermittent network failure or anything which the host is running into GC, or there could be multiple scenarios where the host is simply not able to take traffic for some amount of time, that is still not handled in this situation. So what do we do next for that? In addition to the DNS, what we can do is like we can introduce another component called response tracker. So what this response tracker can do is simply track all the past requests and responses that we have been making to different server IPs from the client. And if it notices that one of the server IPs is simply not able to respond correctly, or like there are errors, or there's a high latency or something, where this response tracker can simply communicate with the client and let the client know that this particular IP, although the DNS says that this IP is up and running, but this based on the past request and response, it looks like we should not send traffic to that. And this passive health check mechanism can detect those bad hosts, and it can solve the problem. So we solve the delayed updates problem because the response tracker can basically now tell you the failures which are happening on some particular IPs. But the DNS issues are still there because the DNS caching still depends on the refresh interval. And if you want to make it faster, it will still have the processing overhead. So what do we do next to solve the processing overhead problem? We introduced the service registry based, the service discovery mechanism, where there is a central registry. In this case, we have Zookeeper, and all the services that we are going to talk to, this service needs to do some sort of registration with the service registry. And the services, whenever they are booting up, they can just simply tell Zookeeper that these are the IPs that we are going to host this particular service. And Zookeeper can maintain a particular mechanism of health check where it will keep on determining that these IPs are up or these are down. And from the client side, what we can do is like we can just set up a connection with the Zookeeper and ask Zookeeper that we want going to talk to a particular service name. Tell me the service discovery data for this particular service. And this lookup is only once, and there is a mechanism of watch on Zookeeper where you can just simply ask once about a particular service to Zookeeper and just tell Zookeeper that if there are any changes, you can just let me know through some update push. So that's like a async callback mechanism where Zookeeper will send a watch to the clients if there are any changes. Otherwise, it will just consider that everything is same and there has been no changes on the server side. So this solves the problem of like staleness because Zookeeper updates are propagated within like 5 milliseconds. It works on layer 4, like TCP layer. It's really, really fast. And now it has less processing power as well because this is a push-based mechanism and you don't have to pull the data unless there are any changes that are noticed by the service registry mechanism for the servers. And at the same time, there will be a consistent view across all the clients because all the clients are going to connect to the same Zookeeper instance, and the Zookeeper service needs to ensure that the consistency is provided across the clients. But after introducing the Zookeeper, what ends up happening is like we might introduce new issues where we have to. So basically, the two major issues that might happen. One is like since it is a registration and push based, and you have to like set up the watch as well and set up the registration. So during the startup, the client needs to fetch all the services and set all the watches that it wants to talk to in the future. And at the same time, this whole mechanism of like registration and push-based mechanism from the different service, that itself can have some bugs and the client needs to be resilient around that bugs. So what do we do for the slow startup issues? So by design, what will happen is like we will be dropping some of the requests during the initial startup, like for while we are setting up all the watches and fetching the data for each service from each of the client, or whenever there is a Zookeeper disconnect and we have to set up the connection and watches again and again, or if there is a client node restart. So in all these scenarios, what will happen is like we have to fetch some data from Zookeeper and set up that particular watch. It will lead to drop of few requests unless like we handle the scenario around it in terms of like blocking call or there are other scenarios. So what we do is like we prefer doing a background fetch for all these services and not do in inline or in any blocking fashion. And at the same time, we maintain a cache of the Zookeeper data at each of the client nodes, and that cache can work as a stale data. So basically, let's say if a service is hosting like is being hosted on 5 servers, and our local cache maintains that copy of the Zookeeper data, and if there is disconnect from Zookeeper and we are making a background fetch, what we can do is like we can assume that those 10 servers are hosting the same service again at the same time, and we keep on sending traffic. So there is some scope of failure, but that is like very less. And since we are already doing a background fetch, it's supposed to be eventually consistent and within a reasonable amount of time. From the publisher side, if the common bugs that we have noticed lately was sometimes the servers are doing late shutdown. What it means is basically server is already down, but it has not been able to, the Zookeeper health check mechanism is not able to figure it out like within the reasonable amount of time. And at the same time, the issue can happen on the startup side as well, where the service is not yet up, but the Zookeeper somehow assumes that the service is up based on its own health check mechanism. And sometimes we have noticed that there are like ghost nodes where that runs into a very weird state because of the shared resources that we have on the same node for different services, and it is running into GC or various kind of process hangups where the Zookeeper and is not able to figure out the health check, but at the same time the service is also not able to respond due to various other reasons. For sometimes it's for intermittent intervals, or sometimes it's for longer durations as well. And of course, like there could be implementation bugs which can be in the whole ecosystem. So what we do is like we reuse the passive health checks that we introduced earlier, basically the response tracker mechanism, and which will handle the in-between states, and which will handle the premature startup or shutdown, and it will be resilient to those failures if it is going on for a longer duration of interval. And at the same time, we introduce another mechanism where we mark some of the hosts as quarantined hosts because they are not able to respond to the request, or they're not able to having a high latency or high error rates. Basically, we will put them into quarantine and do a separate health check from the client side itself. That of course needs to be bounded because the health check mechanism is primarily from the Zookeeper side. And of course, we need a good monitoring and alert system to follow up on these issues and solve. So finally, the service registry mechanism with using the response tracker and quarantine looks like this, where we are keeping tracking the response of all the previous requests to the servers, and using those response tracker mechanism, we are kind of implementing a secondary health check mechanism from the client side itself, and ensuring that we are not sending traffic to the unhealthy or invalid host. So our current scale on this whole mechanism looks like this, where we have around like 1,000+ proxy nodes, and we are talking to 300+ downstream services, and some of the services are having as high as like 7,400 hosts within the same service. And this is of course going to scale, go up as we scale further. And in total, like we are responsible for doing service discovery and load balancing across like 100K+ servers. And at the same time, this needs to be like highly accurate and resilient to the failures that we encounter. So the couple of issues that we still have like, for example, the Zookeeper health check mechanism, since it is per client based, it needs to be converging fast. It takes a while to converge on all the clients. So can we converge faster? Or at the same time, since this is per client basis, if it's possible that one client can discover earlier, then it can share the information with the other clients as well. And this can lead us to do this convergence faster than earlier. And also we are considering service mesh for our upcoming scale needs, and we are trying to evaluate that whether this will help us solve our some of the upcoming capacity needs as well.
All right, thank you so much, Sanjay. So if you guys have questions for Sanjay, then please keep them for the upcoming breakout rooms. And over to you, Jingping.
Thank you, Yulia. And so here please take a minute to take a screenshot of this feedback or open this from your phone here. That yeah, feedback is very important for us to understand if you're interested in any other topics, you want to be part of this meetup event, any suggestion to the team format, let us know. And we are eager to work with you or hear your feedback to improve our meetup event. We will have more meetup events in the future, and we will keep you updated, and really appreciate your feedback. And please don't go away. And Yulia will talk about a breakout session.
Yeah, so first of all, +1 on what Jingping just said, we're trying to build the, very targeted tech communities specific to these topics of interest. And, we would like to continue with these types of events. That's why it is so important to hear from you. And now this is a really, I think, important part of the event, the breakout rooms, the networking sessions, right, in the virtual world, in lieu of being able to do this in person. But now this is an opportunity for you to join breakout rooms with all 3 of our speakers, or the general networking room with LinkedIn. Among others, I will be in that room and will be happy to talk about LinkedIn in general, service infrastructure in particular, and anything else you might be interested in. So right now, you'll see breakout rooms option showed up on the bottom of your screen. So you can go ahead and join the room that you're interested in, and you're welcome to also hop from room to room as well. See you there.
See you in the room.
Thank you.